Hi everyone, welcome to this presentation. Today I will be presenting the entitled paper, Robust Fundamental Frequency Estimation in color noise. My name is Alfredo Esquivel, and this paper is co-authored with Andreas Jakobsson, Jesper Nielsen, and myself, Christensen. So let's going to start introducing the agenda that we will talk about. So I will first introduce the work, give the motivation, then I will give the signal model. I will explain how the parameters can be estimated in a single cascade way. But then I will explain the contribution of the work in the way that we propose to estimate the parameters. Then I give the experimental setup with the corresponding results, and finally I conclude the work. So fundamental frequency is a very important quantity in multiple speech applications, such as music transcription, audio coding, and speech decomposition. Correlation-based methods are traditionally used, but they may suffer from octave errors. They are not robust to the noise, and they may have problems in low values of the fundamental frequency. So it's suffer for time frequency resolution problems. By other side, parametric methods are more robust to the noise, but they are typically derived under wide function noise assumption. So therefore, they may present problem of octave errors in color noise conditions. In such case, the spectral shape of the noise needs to be considered. In that case, the maximum likelihood solution would no longer be equivalent to the NLS estimates. So here we propose to approach to estimate the speech signal and the noise parameters in an iterative manner so that the accuracy can be improved. So this is a reminiscent problem of the mixed spectrum estimation problem, which tries to jointly estimate the signal and noise AR parameters in a nonlinear multidimensional optimization problem. That would be the most computationally complex way of solving the problem. Therefore, people have tried to use alternative ways. So for the case of independent sinusoids, the sinusoidal and the noise AR parameters are estimated separately in two different steps. And this constitutes just a single iteration. So for the first step, sinusoidal parameters are estimated, each one at a time, using iterative algorithms such as matching pursuit or relax. And it doesn't care about the noise spectral shape, and even the noise is colored. This one-step iteration solution will result in statistically efficient estimates. But this is not possible for harmonically related sinusoids, and one should therefore exploit the harmonic structure to allow for improved estimates. But even worse, if hearing the problem one ignores the noise AR structure for estimating the fundamental frequency, it will increase the risk of selecting the wrong peak. So octave errors may appear. So here is the signal model that we are using. So the noises vector is formed by the harmonic model plus AR model of noise. So the harmonic model implies that the voice pitch segments are described by L harmonics, in which each one has a frequency which is an integer multiple of the fundamental frequency, and they are also described by the complex amplitudes. And the noise is modeled as an AR process. So here P is the order of the autoregression, and these AIs are the different AR parameters. Well, here in the case that L is equals to 0, then it implies that the segment is not voice or which is on voice, pitch, or pauses. So here in vector notation, if we collect ensamples in a vector, then we have this model in which the harmonic model is described by this set L matrix, which has two L columns. In each column, it contains a complex exponential associated with one harmonic. And this alpha is the complex amplitude vector. As I said, if L is 0, then it's not voice segment. So for a single cascade estimation, this has already been done in this work. We do a first pre-whitening signal step. First pre-whitening, because otherwise we will observe a high number of gross errors and those in detection errors, especially at low SNRs. The way that we do pre-whitening is by trying to fit an AR spectrum to the estimated noise PSD. So this can be done with typical noise trackers as MS and MMSE based on speech rest probabilities, which work well when the noise is stationary, but for non-stationary noise, taking into account priori spectral information of speech and noise sources is of more benefit. So this recently introduced colorimetric NMF approach. Then this AR pre-whitener, which is updated in a segment-by-segment basis, is applied, and this operation will not modify the fundamental frequency. Now the noise is rendered closer to white, so an initial fundamental frequency can be obtained from the nonlinear least squares estimator. So among a grid of possible fundamental frequencies, we search which one is the one which maximizes this projection energy over the subspace spanned by the columns of set in this way. And this can be solved in a rapid order recursive manner, so it's not slow anymore as it was 6 or 7 years ago. It's fast now. And at the end, L is selected from model selection criteria, such as evaluation information criteria. Now we discuss how we can estimate the parameters. So the first approach is an approximate maximum lighting one. So now we have the different harmonics of the fundamental frequency estimated, so we can estimate the corresponding least squares amplitude, and the residual noise therefore can be formed because we have a full parameterization of the signal. If L was 0, then the observed vector would correspond to the noise in such case. So directly from this noise vector, we can estimate the AR noise parameters using autocorrelation method of AR modeling. And therefore, we can apply these probability coefficients to get a new probability signal vector. So we get a new fundamental frequency estimate. So that's why it's hat here. And the order. So this is possible from a rapid implementation, as I said. And we can go back between these steps until convergence with either NLS cost function between 2 consecutive iterations is below a threshold value or maximum number of iterations reached. If the model paper was the L0 harmonics, then we check if in the next is still detected as not voiced, and then the process is stopped for that second. A second approach is based on linear filtering. So we can estimate the speech vector by applying a filtering matrix. So it affects both the harmonic model part and the noise part. So we want to minimize the power of this term, which is this one, subject to the constraint that the harmonics pass undistorted. And this solution is given by the Lagrange multipliers, and it results in the LCMB filter, which depends on the inverse of the noise covariance matrix. But since we already have AR parameters estimated, this can be parameterized by the Jakobsson formula, which depends on these upper triangular Toeplitz matrices, whose first rows are parameterized by these AR coefficients until up to 0, until we match the desired size of this covariance matrix. And similarly to the approximate ML, we can iterate between harmonic signal and AR parameter estimation until convergence. The testing was done on the KILL database, which has an estimate, which represents and estimates the ground truth obtained from autocorrelation-based methods. We compare to the classical non-parametric GIF, RAP, and Jakobsson, which have at the end a final step of refinement as median filter of dynamic programming for the proposed. And for these ones, we obtain pitches in the interval 62 4-folded with a maximum possible 27 in the harmonics in the proposed ones. The noise which were added were bubble factor and F16 at these ISNRs. We ran 6 Monte Carlo simulations per kit file. So there were 10 files, so in total 60 per ISNR at each noise type. And the initial applied per whitener is based on a parametric NMF, which is more robust in non-stationary noise conditions. And for this one, we use an autoregressive order of 25. This required a previous offline training stage of the spectral basis matrix of typical speech and noise envelopes. We should point out here that we also train on the same noise types. We do the test but with using different samples. We also train on street noise, and the speech spectral envelopes were trained on a moderate database different from the tested one. For assessing the performance, we are interested in gross error ratio, which only takes into account voice raised by both the estimated and the ground truth, but also we evaluate the voice detection errors. These are mutually exclusive, and these both types of errors can be included in the full frame error rates. Here I have an example of a male speech contour, a male pitch contour before Reestimation, and from the Reestimation, the black circle is the ground truth, the blue point is estimated value. So we here see that without the Reestimation, we have a lot of octave errors, which are further corrected if one applies the approximate maximum value. So here, less blue dots appear, so they are corrected here from the iterating steps. Here I show for a female speech contour at 15 dB in factory noise, and we here see that, especially in these black circle areas, that many values which are supposed to be detected as not voiced are detected as voiced here. So here, and here. But if one applies the LCMB iterative filtering approach, one can see here that the blue dots are covering more this area, so they are corrected and detected as not voice. So yeah, the reiteration here is improving also the voice detection accuracy as well. Here I have the gross error ratio, the first row. So we see that the proposed approaches, here is without reiteration, and these are the two iterative approaches, offers better performance than GIN and RAT at all ASNRs. Here at 15 dBs, only if the reiteration is done, we outperform RAT. Compared to Capstream, Capstream has lower gross error ratio, but it has higher voicing detection errors. For bubble noise, we have, even without reiteration, better voicing detection than all the three non-parametric methods. Compared to factory, to GIN and Capstream, at RAT, at -5 dBs. At 5 dBs, we observe similar voicing detection errors from the proposed Reestimation. And at 15 dBs, RAT seems better. But in terms of full frame errors, we can do better than RAT at -5 and 5. At 15 is similar. And also in factory and X16 is better the proposed than GIN and Capstream. For bubble, we see better than GIN and RAT in all conditions. To Capstream, we observe similar performance at low SNRs, but it's better at high SNRs. So here we see that in most scenarios the proposed is better. So just to conclude the work, we see here that parametric estimators as NLS are only statistically efficient in white Gaussian noise conditions. But the NLS estimator, which has a rapid implementation, is still useful as long as the deep noise shape is taken into account forming after white filter. So we here see that the fundamental frequency with the model order and amplitudes with the AR noise parameters need to be estimated iteratively, so that the risk of octave errors and voicing detection errors is reduced noticeably. And only when the reiterations are applied, the proposed approach has a better performance than state-of-the-art fundamental frequency methods. Even if the proposed does not take correlation of consecutive estimates into account, is more robust to the noise. So thank you for listening.